Hi, this is our project on a reaction kinetics analysis tool. We developed a MATLAB GUI that combines Arrhenius regression with first-order reaction simulation to analyze how temperature affects reaction behavior over time. The goal of our project is to build an interactive tool that takes experimental
It's fine. You can just restart. That's the beauty.
Wait, I don't get it.
What?
So, what do you mean restart?
I'm just going to go into
You're
the
just gonna
actual
clip it?
file. Yeah.
Okay. The goal of our project was to build an interactive tool that takes experimental kinetic data, fits an Arrhenius model, and uses it to calculate a temperature-dependent rate constant. The user can input initial concentration, temperature, and simulation time, and then the program will simulate reaction progress using either a numerical ODE solver or an analytical solution. Overall, the tool connects experimental data to real-time reaction predictions with a simple interface. Our model is based on the Arrhenius equation, which relates the rate constant to the temperature, and we linearize it to the natural log of k versus the inverse of temperature, which allows us to use linear regression to estimate the activation energy and the pre-exponential factor. Once we calculate the rate constant at a given temperature, we use a first-order reaction model where concentration decays exponentially over time. We also compute conversion, which shows how much of the reactant has been consumed, increasing from 0 towards 1. This flowchart represents the full logic of our program from data input to final output. The process starts by loading an external file that's named Arrhenius data. This data set is structured with two columns, temperature in Kelvin and the corresponding experimentally measured rate constant. The data must be clean and positive because we apply the logarithmic transformation later. After loading the data, the program transforms it by computing the natural logarithm of the rate constant and the inverse of temperature, which allows us to linearize the Arrhenius equation. Using this data, we apply linear regression to determine the slope and the intercept, which are then used to calculate the activation energy and the pre-exponential factor. Next, the user provides inputs through the GUI, which is initial concentration, batch temperature, simulation time, and the desired solver. The program uses the Arrhenius model to calculate a new rate constant at selected temperature. At this point, the program branches based on the solver decision. If the numerical option is chosen, it uses the ODE 45 to solve the differential equation for concentration over time. Otherwise, it uses the analytical exponential decay equation. Once concentration is computed, the program calculates a conversion as the secondary output, and then the results are displayed through a dual axis plot showing both concentration and conversion, along with a summary table.
This slide shows the main graphical user interface of our program. The user inputs the initial concentration, reactor temperature, and simulation time through numeric fields. There is also a drop-down menu that allows the user to select between a numerical solver using ODE 45 or an analytical solution. Once the inputs are set, the user can run the simulation, which triggers the full workflow of loading data, fitting the model, and generating outputs. Here is a sample output from the GUI after running the simulation. The program displays a plot showing how concentration decreases over time, along with conversion increasing towards completion. It also shows key calculated values such as the rate constant and fit quality, along with a table that summarizes numerical results at selected time points. The program visualizes results using a dual axis plot where concentration and conversion are shown on the same graph over time. This allows us to directly observe how the reaction progresses. In addition, a table is generated within the GUI that lists sampled values of time, concentration, and conversion, making it easier to interpret the numerical results. Our program uses both statistical and numerical methods. First, we apply linear regression using MATLAB's polyfit function to fit the Arrhenius model and determine the activation energy and pre-exponential factor. Then, depending on the user selection, we either solve the reaction using the ODE45, which numerically integrates the differential equation, or use the analytical exponential solution for a first-order reaction. This allows us to compare exact and numerical approaches within the same framework. The program also uses logical statements and repetition to control execution. Input validation ensures that all values are physically valid, such as preventing negative concentrations or temperatures. Conditional statements are used to select between the numerical and analytical solvers. Additionally, repetition occurs in the numerical solver and in sampling data for the output table, allowing efficient handling of large data sets. This project incorporates several MATLAB features beyond basic scripting. We use UI figure and related components to build the graphical user interface, including input fields, drop-down menus, and buttons. The program also uses read table to import external Excel data, UI table to display results, and UI alert for error handling. Additionally, we implemented ODE45, which is a built-in numerical solver for differential equations.
Hello everyone, I'm Abraham. For the conclusion of this project, we decided that the overall objective of this tool would be to correlate the erroneous regression with a reaction simulation. This basically predicts how the reaction would take place if we changed either the temperature or the concentration. We learned how to create the GUI. We learned numerical ODE solving along with regression and the data visualization in MATLAB. So for the demo here, we run the simulation and it imports the points from our data. This is basically how the erroneous reaction takes place in basic and normal results. However, what we can do is change the starting factors, like the initial concentration or the temperature of the reactor. And we can also change how long the simulation runs. Since we know how the reaction takes place at standard conditions, we can have the simulation predict how it would react in different concentrations or temperatures. Basically, we kind of ran a best fit line, and with that best fit line, we can change some aspects of it.